Hello and good afternoon, scholars. Welcome back to Mr. Sniffen's geometry class. Today we are talking about the distance formula. Our formula that we're going to be using today allows us to find or quantify the actual numerical distance between two different points on a coordinate plane. As you remember from our previous lessons, our coordinate plane is made up of x and y values, this personal rationale of like how far to the left something is, how far right, how far up, how far down, our x and our y values. When we think about distance on a coordinate plane, it's a little bit different than how we normally experience in our life. We've talked previously before about using New York City or a grid-based system as a means of trying to rationalize distances. We described like one way how to go uptown, say from Little Brazil up to say Harlem where our school is. We had to kind of dictate or rationalize how many individual streets we went up and then how many streets we went over. Because in New York City, I don't know about you, but I don't own a helicopter, so I can't go over buildings. So normally we're going to have to go one direction at a time. In a coordinate plane, though, we're able to go diagonal. We don't have to follow the grid-based system. But when we do our calculation for our distance, we will still take into consideration how far left or right we're moving, what our x value is, what our x length is, and what our y length is, how far up and down we're going. So let's take a look at our notes for today, just to go through this nice and quickly for you. Along the top of your page, as always, our title, the distance formula, today's date, July 17th, and we have just one of one pages. Pretty short one for us today. When we're looking at our definition here, we're talking about, for the distance formula, it's used essentially just to find the distance between 2 points. Way that we go about quantifying that distance formula is we're combining our x and our y values. We're finding the difference between our first and second point, that subtraction statement, and then adding them together. So let's look at the actual formula itself. Here we have lowercase d, our variables are typically lowercase, just like in our y equals mx plus b equation. But we have distance is equal to radical, in parentheses, x2 minus x1, close our parentheses, squared, plus y2 minus y1, parentheses closed, squared. We're going to add those squared values together, go through all of our radicals, come out at the end. Sorry, we're going to square everything, come out the end, hit it with a radical, and get our answer. One thing to take in consideration when looking at this formula is when we think about our orders of operation, our PEMDAS, if you will. PEMDAS doesn't have radical in it. So what we're really doing here in this equation is we're doing everything under our radical first, and then we're going to find the square root of it. What you'll see that's almost like counterintuitive here, but will make sense in a second, is that we have a square and a radical. Why would we do that if we're just going to basically put it back together in the same exact fashion? Well, here's the point. In a coordinate plane system, we actually have negative distances. We can have a value of -5, -12 for our x and our y. For people, for a normal experience, we don't normally quantify distance as negative. We either say we didn't move or we moved away from something or into a specific direction, but we'd normally quantify that in a positive. In our coordinate plane system, though, we have negative values. So let's look through just our steps here. When we're using our distance formula, we can only measure the distance of something that we would call like a segment or a portion of a line. Lines themselves are infinite. So we're going to have two endpoints or 2 points that we're going to use to find the distance between. Our second spot here is we're going to pick a point to label our x1 and our y1, or x2 and our y2. Normally, and there's no specific rule about this, but typically what you see on the left-hand side is we're going to label our x1 and our y1. On the right-hand side, our x2 and our y2. Doesn't matter though. We're doing all that squaring. We're finding our square root. The negative, the positive, it all comes out basically the same in the end. Lastly, as always, we're going to insert our numbers into our formula. Let's take a look on the screen. We're going to use Delta Math once again. Hope you guys are liking that website. And as always, if you have questions, things that pop up about Delta Math, some of the quirkiness that might appear, shoot me a message and I'll help make sure we get everything set up for you. But with this particular example, what we have in front of us, we have 2 points. We have those 2 yellow points. We can imagine in this question, it could be drawn as a segment or just a portion of a line, but we want to find the distance between these 2 points. What I'm going to do is I'm going to take that point that's on the top left, that 3, 9. I'm going to just put that as my x1, my y1. That next point on the right hand side, that one, if you're looking closely, that's 9, 5. That's going to be our x2 and our y2. In terms of our steps, we're going to set up our equation here. Distance is equal to our x2 minus x1 in our parentheses squared plus y2 minus y1 parentheses squared. Technically speaking, you want to extend that radical line all the way out, but oftentimes we'll just see like just a short radical. Don't be worried. Now let's insert our values here, our x2, and this is why I like to just like label everything out. Like here we have on the left hand side, as opposed to just like looking up, like continuously looking back and forth on the graph, because it increases your chances of making a mistake, I feel. I like having everything nice and set up. I'm going to do 5 minus 9. All right, so 9 minus 3 gives us 6 squared. Remember, take that down with us. 5 minus 4 gives us negative 4. And here's where this negative number kind of comes into play. Once we end up squaring that negative 4, we're just going to end up getting a positive 16. So that's why we're using this square notion, so we could, when we go ahead and regurgitate our answer, when we spit it out at the end, we have a positive value. Because really, we don't talk about distances in a negative. All right, so now that we got our squares out of here, technically, we're still under a radical, but we have to combine everything first. 36 plus 16 gives us a nice and easy 52. If you look on the Delta Math website, for this question, this picture, it asks us to find the distance between 2 points, leave it in simplest radical form. Depending upon the computer software, your simplest radical form might be something slightly different. It depends what they're accepting as your answer. Realistically, this radical 52 can be broken down further. Remember, back to Algebra 1, kind of what we're going to do here is we want to find common denominators with 52 and having one of them be a perfect square. Whenever you see an even number, like I always think, okay, all even numbers are divided by 2, and then half of those even numbers can be divided by 4, and 4 is going to be our first perfect square. So you can try out 4, see what that multiplies to, and see if it works to 52. In this particular example, we can do radical 4 and radical 16. Sorry, radical 13. 4 times 13 gives us 52. If you go ahead and try some of your other numbers for your perfect squares, 3, which is 9, 4, which is 16, 5, 25, 6, 36, none of those numbers conveniently go into 52. They give us a decimal. So what we're going to do is basically break this radical 4 down one more step into just a plain old 2, and we have 2 radical 13 as our final answer. It's equal to our d, or our distance. In regards to our distance formula, the main thing that we want to take away is that we're basically, kind of as the name implies, we're just looking to find the amount of space that exists between 2 points. The distance formula is unique in that when we're talking about the coordinate plane, we can have negative values, but considering the structured mechanism of the formula, where we have that squared values, those potentially negative squared values, they end up becoming positives in the end. So don't fret if you have a negative answer. By the time you get to the end, it should be positive. If you think you have a negative distance, well, then you've made a mistake, and you got to go through and look at your equation and whatnot again. But with the distance formula, really the main gripe, the hardest thing is kind of remembering exactly what the formula is. And that's why today, when you're going to be practicing, you're going to be doing about 10 different instances. As I've said throughout the school year, and for those of you who haven't had me, my favorite math teacher, Miss Nicholas, used to give us like 30 questions a night, and that's how you get this information ground into your head. You just keep doing it over, over, and over, repetition. Like if you're learning Korean language, Spanish language, using flashcards, things like that, it's all about turning that short-term information into long-term. And doing long-term is often through repetition. So if you have any questions, things like that, please feel free to reach out to me during office hours today, call and text, anything like that. We can talk about whatever you want. Until next time, once again, please wear a mask. Um, don't launch fireworks off. Everyone's getting their house burned down. Please don't do that. Okay? It's too crowded here. All right. Stay safe and have a nice day. Bye.